All right, chapter 11, and like I said, we're not going to do all of chapter 11. Chapter 11, you know that integral thing I had on the board? They actually do integrals in here, and that's the second half of calculus. Like, you have to know a whole bunch of calculus before you get there. All right, so we're going to just focus on limits this chapter. And you've heard of limits before, a couple of ways. One, we did limits in here. We did them when we talked about rational functions. Do you remember that? Like, we had a rational function, let's say it had an asymptote here, and we graphed it like that, and maybe it had like an asymptote here, and we graphed it like that. And we talked about the limit as x goes out to infinity. Do you remember that? Remember, as x goes to infinity, we found that the limit was equal to 2 because that was the asymptote. That's going to be coming up. That's going to be 11.3 part D. We'll talk about infinity asymptotes and stuff like that. All right, so today we're going to focus on 11.3a. We're just going to focus on limits using 3 different things. So limits using direct substitution. You'll like that. It's like you just plug a number in. Direct substitution. We're also going to do limits on our calculator by graphing. You'll like that too, because it's on your calculator. You don't have to graph those by hand. And we're going to do limits by looking at their properties, using properties of limits to solve. This stylus is not working for me. Properties. Oh, that's so much better. Sort of. Okay. All right. Here we go. So let's go ahead and talk about what a limit actually is. Now, back in the day, they used to give you a really bad definition of a limit. It used epsilons and deltas, and it was really confusing and horrible. Now they give you a nice, easier thing. They call it an informal definition. So this is what a limit is. If you have the limit as x approaches c for some function f of x, and it's equal to L. Okay? What does all of that mean? Well, this is what it means. It says here that as the values of x, so you have an f of x function, a graph. And as your values of x are getting closer and closer to a constant c. So as the values of x get closer to c, so it could be getting closer to 2 or negative 10 or 3 or whatever, pi, who knows. As the values of x get closer to c, the values of f of x, so like the y values, the values of f of x approach L. Now that's going to be the most important word in this informal definition of a limit. Approach L. Now, approaching something doesn't mean it has to equal that. For example, the street. I tell my kids to stay out of the street, right? And that little guy, he likes to approach it as close as he can get to the street before going in. But the street is the limit. It's how far he can go. So he approaches it, that's it. Doesn't mean he touches it, okay? All right, so let me give you 3 graphs to kind of show you what this means. So here we go. Draw this graph. 1, 2, 1, 2, 3, 4. And we're going to put a dot at 2, 4. And then let's say the graph goes like this. Whee! And it goes right through 2, 4. So there's our graph, okay? There it is. Basic. Very basic graph. Does some weird stuff. Who cares what it does? But we're going to take the limit as x approaches 2 for f of x. We call this the graph y equals f of x. And we're going to take the limit as x approaches 2. So let's talk about what that means using our informal definition of what a limit is. As x gets closer and closer to 2, the values of f of x approach what value on f of x? So as I'm going closer and closer to 2, here's my magical number, closer and closer to 2 from both sides, what is my f of x approaching? 4. Perfect. The limit is 4. Now, it just so happens on this graph that f of 2 equals 4. Okay? It's not a requirement, though. You don't have to equal what you're finding the limit of. But it just so happens on this one it does. Okay, let me show you another graph. Here we go. Try this one. Same point at 2, 4. What we're going to do is we're going to draw an open circle there. And then we're going to draw f of x. Okay? Who cares what it does? There it goes. Okay? So there's f of x. Y equals f of x. And now what we're going to do, same thing. We're going to find the limit as x approaches 2 for f of x. So using this same definition that I gave you, as we're getting closer and closer to 2 is our magical number, we're getting closer and closer to 2 on this side and that side. What is my y value approaching? 4. The answer is 4 again. You're like, but wait, how can it be the same? They're not the same graph. You know what? I've told people over the years what you do. You cover up 2. If you're trying to find the limit as x goes to 2, you don't care what's happening at 2. If I cover both of those up, they're exactly the same. I'm going towards 4. Okay. And then if I were to say, what is f of 2? Well, f of 2 doesn't exist. There's no value. There's no y value at x equals 2. There's a break in the graph there. So these don't have to be equal to each other. The last one they were. The value of 2 was 4. Okay? But here it's not, but there's still a limit. And people will say the limit doesn't exist there, but it does. Okay, it's approaching 4. It doesn't equal 4, but it's approaching 4. All right, now here's this last one. Same point, 2, 4. We're going to put an open circle there. We're going to draw our f of x. Whee! I have to say that every time. I don't know why. And then what you're going to do is this. You're going to put a dot at 2, 1. Okay? All right. Now let's find the limit as x approaches 2 for f of x. Okay, so jump on your graph. Someone in my last class shouted out, it's 1. I was like, is it? Talk about the definition. Okay, as my x's are getting closer and closer to 2 for my x, what are my y's approaching? Guess what? 4. Cover that up. What are they approaching from both sides? 4 still. Okay, now it just so happens on this graph that f of 2 equals 1. But like I said, these don't have to be equal to each other. It's whatever it's getting closer and closer to. So if I'm walking on this graph, here I am, I'm walking on this graph, am I approaching 1? 1's way down there. I'm walking here, my y values are, so my y values right here, it's 2, then it's 3, then it's 3.99999. Over here, you know, it's 5, and then they're approaching 4, the y values are. Do you see that? Pretty cool, huh? So that's kind of the 3 things that we're going to do. This first one is direct substitution. You can just plug the number in. You actually get the answer. Here, we're going to either graph it or do algebraic stuff. Algebraic stuff is tomorrow. That's my favorite way to solve. Okay, yeah?
How do you know which one to do?
What do you mean?
I don't know.
Like, no, they'll give you f of x. So this is just 3 separate examples of what you could be given. But their answers are all the same. You're trying to find what it's approaching.
They all approach 4.
Yes.
Yeah.
Mm-hmm. All their answers are 4.
Yeah.
Yes. You got it. You love this stuff. So far, you love it. All right, so let's do direct substitution. Direct substitution is pretty simple. Literally just plug the number in and it works, okay? All right, so let's do a pretty easy one. Number 1, let's find the limit as x approaches 2. No, let's do a different number. Limit as x approaches 5 for 3x minus 2. Okay. A lot of times we're going to do these graphically, but if they tell you to use direct substitution or algebraically, you cannot graph this. But you know what the graph of this is. If you were to graph f of x equals 3x minus 2, that's just a line. Are there any weird stuff going on in lines? No. The domain is all real numbers. go ahead, plug 5 in, and the limit is what? 13. Okay? 5 times 3 is 15, minus 2 is 13. Direct substitution is you directly just plug the number in because it actually has a y value, and that's the limit there. All right, let's try another one. Number 2. Ooh, how about this one? The limit as x approaches 0 for e to the x minus tangent of x over cosine squared of x. Okay, so I just gave you 3 things we haven't done in a while, right? This is all non-calculator, by the way. Yes! It's good. You should know these things. Yes. It kind of combines all the stuff you've learned together into one problem. All right, so let's do it. Just take it individually. Plug in x is 0. What is e to the 0? 1. Okay. What's the tangent of 0? 0. I don't know. Okay, tangent of 0. Let's talk about tangent of 0. You can look at this 2 ways. Do you remember this thing called the unit circle? No? No. All right, if you go to 0, right? 0 degrees, 0 radians, whatever. It is the y value over the x value. If you're on the unit circle, this is the point 1, 0. So tangent is 0 over 1. Okay? Or you can think about the tangent graph. Do you know the tangent graph? The tangent graph goes through the origin. So what's that point right there? 0, 0. When you plug in 0, you get 0. Okay, how about cosine? Yeah?
What if you give us a number like x goes
Ooh.
to 4?
Oh, I wouldn't. Not for that. It would have to be like pi over 2 or something that you know how to do. You're like, even then. Okay, cosine squared of x is the same thing as cosine of x squared. So what is the cosine of 0? It's 1. And then 1 squared is still 1. So you get 1 over 1, and so the answer is 1. So direct substitution is nice. It works. How did we get 1 for cosine of 0? You can look at your unit circle. It's the x value. It's 1. You can also think about, does anyone think about the graph of cosine? The graph of cosine looks like that. So at 0, you get the point 0, 1. Same thing. Okay. How about this one? You get to be mad at me again. Number 3. How about, we'll go like this. We're going to take the limit as n goes to 16. It doesn't always have to be x. I'm just going to throw out a different variable for you. N goes to 16 for the square root of n plus 3 over log base 2 of n. Okay. You should be able to do this, yeah? No? Not by hand? Okay, this is just direct substitution. There's nothing weird going on here. We're going to plug in 16. So you get the square root of 16 plus 3 over log base 2 of 16. So let's go ahead and fix this. The square root of 16 is 4 plus 3 is 7. And do you know what log base 2 of 16 is? It's 4. Yeah. Remember that? 2 to the what is 16? 2 to the 4th is 16. So your answer is 7/4. Beautiful. You love these so far? No. Okay. All right, so let's move on. Part C now. We're going to use our graphing calculator. So go ahead and get your calculator out, and we're going to solve these by graphing. And you're like, no, I'd rather not. I'd rather just solve it by direct substitution. Well, these you can't. That's why we have to graph them, okay? All right, so let me go ahead and tell you, sometimes limits don't exist, okay? It doesn't happen a lot, but sometimes it does. So let me show you how limits can fail to exist. Limits that fail to exist. Because a lot of times when people can't get an answer, they think the limit doesn't exist, and they're wrong. It does exist, it's just you can't find the answer, okay? Now, we all know Lindsay Lohan in Mean Girls. She said the limit does not exist, and you know what? She was right. I paused that DVD, and I worked out the problem like everyone else did, and she was correct. The limit didn't exist. So why didn't it exist? Well, there are a bunch of ways that limits fail. Number 1, if your limits are approaching 2 different y values, then the limit doesn't exist, okay? So for example, let's say I have the graph f of x equals the absolute value of x over x. And I want to take the limit as x goes to 0 for this function. Well, if you plug in 0, you're going to get 0 over 0. What does that mean? I can't divide by 0. Oh, limit does not exist, okay? This one's actually true. It happens to be that this graph goes like this. Okay? Interesting graph, kind of boring, but when you plug in 2, you'll get 2 over 2, which is 1. When you plug in negative 2, you'll get 2 over negative 2, which is negative 1. So this graph really only has answers of 1 or negative 1. So as I'm going to 0, well, what's the limit? Well, the definition says as I'm getting closer and closer to x equals 0, what's my y value approaching? Well, it's approaching 1. No, I'm over here now. What's it approaching? It's approaching negative 1. So when 1 and negative 1 don't equal each other, guess what? The limit does not exist. Okay? But as long as you're approaching the same, then you're fine. So that one, the limit doesn't exist. Another way limits don't exist is if, you don't see this very often either, but let's say it oscillates. It oscillates at whatever point you're trying to get to. So in other words, something like this happens where your graph's going like this, and then in here it goes. Have you ever seen a graph that does that? It's really interesting. But what happens is it's not landing on something. So as I'm going, x is going towards 0, my graph is like bouncing between two numbers. It's oscillating. It's never going to be a limit there. Okay. Also, limits that go to infinity or negative infinity. Some people will say that the limit is infinity. Like, for example, let's say we're trying to find the limit as x goes to 0, and we have this graph that goes like that and like that. Some people will say the limit doesn't exist, but some people will say that the limit here equals infinity. I'm okay with infinity or does not exist. The book kind of says both. It's weird. Now, if you're going to go to calculus next year and you're going to take AP Calc, then you really want to say the limit's infinity, because that book really says that. Now, if they're going to separate infinities, like if it's going towards infinity and negative infinity, then yeah, the limit here does not exist, because this is going up to positive infinity, that's going to negative infinity. Those are obviously not the same y values. Okay? All right, now knowing that, those are limits that don't exist. We're going to do some that actually do. I don't think any of your answers tonight are limits that don't exist. So let's do this one. What number are we on? I lost count. 4. Thank you. All right, number 4. Let's go ahead and find the limit as x approaches 0 for sine x over x. All right, and so you think, okay, I want to use direct substitution because that seemed pretty easy. All I have to do is plug 0 in. Well, if you do that for this one, you end up getting 0 over 0. And so you're like, oh, limit doesn't exist. Wrong. Okay? 0 over 0 is not your answer. D and E is not your answer either. There is a limit here. We're going to graph it. So go ahead and get your calculator out. Make sure you're in radian mode for these. And we're going to graph y equals sine x over x. And hit zoom 6. Get a normal graph, and that's what it looks like. Okay? I'm going to zoom in on that because I can't really see what's happening here. So I zoom in, and it looks like there's actually a y value there, but there isn't. There can't be at x equals 0. So hit trace, and if you plug in x equals 0, then the y value is blank. Can you see that? Not really, huh? There you go. See how the y value is blank? Now, does that mean the limit does not exist? No. Okay? What we need to do is we need to look at either side of this graph and see what my y value is approaching. You can see it. What's y getting closer and closer to? 1. The limit's 1. So if you were to hit trace and you plug in 0.000001, you know what your calculator does? It tells you that it's 1, even though it's really not. It's so close to 1, they have to tell you 1. If you go negative 0.000001, that's the other side, guess what it tells you? 1. And so as close as you're getting, it's approaching. It doesn't have to equal. It actually doesn't equal. But your answer to this is 1. So the limit as x approaches 0 of sine x over x is 1.
Okay, why does substitution not work?
Because, try it.
I know it doesn't work, but why? Math should all work, right?
No, because there's a hole there. There's a hole in the graph. This graph looks like this. Direct substitution only works when the limit is actually equal to the value of that function. So like the limit as x goes to c equals L, it only works when you have that. That's direct substitution. You actually plug in c and you get the y value at that point. This has no y value at that point, so you cannot use direct substitution. There's a hole in the graph. How am I going to plug in an x value when there's no y value there? You can't.
Yes.
Yeah, you can guess. Guess works sometimes. But graphing works really well for those problems. And you know, we're going to find out that you can do a lot algebraically too.
Okay, so are we going to have our calculator the whole time?
There's going to be parts that are non-calculator.
Like we're actually going to have to like, go on the floor.
like those ones that we did, the direct substitution ones, you won't have your calculator for those. Yeah.
On the test, are you going to tell us whether the graph or substitute?
Yeah. Okay, so like for this example, the next one that we're going to do would be something like this. The limit as x approaches 3 for x squared minus 9 over x minus 3. Okay, we're going to learn tomorrow how to do this one algebraically. I like algebraically better. I just like algebra better than graphing. But this one right here, if you tried direct substitution, you would, once again, you plug in 3 and you would get 0 over 0. Okay? 0 over 0 does not mean the limit does not exist. This right here, I don't know if you remember, but when we graph this, there's going to be a hole in the graph at 3. Okay? So let's go ahead, let's do this one graphically, because we're allowed to. Tomorrow we're not allowed to, but today we can. We're just getting used to limits and what they are. So x squared minus 9, make sure you put that in parentheses, divided by parentheses x minus 3. I'm going to hit zoom 6, and it looks like a basic line. It's like, oh, okay. But when I hit trace and I go to x equals 3, there's no y value there. There's none. Okay, so how am I going to find it? Well, plug in something very close to 3. What's very close to 3? 2.99999. What do I get? I get 5.99999. Okay? Now plug in 3.00001. And I get 6.0000. Well, what's in the middle of those two numbers? You know, it's going to be kind of obvious. So when I plug in, let me write this down. When we plug in x equals 2.99999, we got that y was 5.99999. When we plugged in x equals 3.0001, so we're really zeroing in. We're trying to get closer and closer to x is 3. We got that y was 6.0001. Now the answer is not either one of those. The answer to this is exactly 6. Okay? Now, graphing's not all that great because you just saw, like, it didn't give me the answer I was looking for. Tomorrow, we're going to factor this, we're going to reduce, and then we're going to substitute in. It's so good. Think about it. Can you picture that in your head right now? Okay, I'm going to go off on a little tangent. This is a spoiler alert for tomorrow. X plus 3, you can? X minus 3, guess what? Those reduce. Then use direct substitution. Your answer is 6. Beautiful. Isn't that so much better? That's yeah. Some of them you can't do. Like the last one, there's nothing algebraic that I can do to that. Yeah. But this one, yeah. When you can, you want to, and you will. You will. Don't you worry. That's a little something to look forward to tomorrow. It'll get you out of bed in the morning. You know, like, ooh, we're gonna do these algebraically today. Okay. No, not so much. Okay. All right, so that's graphically. Now we're going to do the last part, which is using properties of limits. Properties. All right, so limits have some properties, and they're pretty good to use them. This property wasn't in the book, but I think it's a really good one. If you take the limit as x approaches c for f of x, no, don't write f of x, of a constant k, Okay? Limit as x approaches c for a constant k. Your answer will be that constant. Okay, that should make sense to you. Like, for example, let me give you a little example over here of this. Let's find the limit as x approaches -4 for 5. Okay. Think about this one graphically. Like, you can't plug -4 in. I mean, you kind of can, in a way. When x is -4, what does y equal to? 5. Y equals 5 is just a horizontal line. As I take the limit as x goes to -4, guess what y is approaching? 5. Okay, it's always 5. It doesn't matter if x is approaching 3 or 12 or 1,000. Y is always 5, so that's what the limit's going to be, 5. So anytime you're taking the limit of a constant, it's just going to equal that constant. Okay. Another property is all of our operations. So like, for example, if we have the limit as x goes to c for some function that the limit exists there, okay? We have to say that the limit actually exists. And if we do this, and we do plus or minus or times or division, basically you can split it up. This is equal to the limit as x goes to c for f of x plus the limit as x goes to c of g of x. Okay? And that plus in the middle works if it's times, divide, subtract. Do we need to write all of those down? Do you want to? Like, let's do this. So this right here is plus or minus. It would be plus or minus depending on what it is, okay? Let's write down the multiplication one. If we have the limit as x goes to c for f of x times g of x, okay, or divide, it doesn't matter. They're all going to be the same. It's just you can take them individually is basically what it says. So limit as x approaches c for f of x times, that looked like composition, but it's not, the limit as x approaches c for g of x. Okay. Why would you want to do that? Well, I'm going to show you in a minute. We're going to use our properties to solve some limits, okay? There's also, like, if it has a radical, you could take the radical out to the front. So let's write that one down. I didn't earlier, and I kind of regretted it. All right, so if we have the limit as x approaches c, and you're taking the limit of the nth root of f of x, okay, then this is going to equal the nth root of the limit of f of x as x approaches c. Okay? All right. So let's do some. Here we go. Number 6, around 6, 5, 6. That was a 6. Okay, let's have a minute bell. All right, so number 6, this is going to say using, you cannot graph these, no graphing, okay? We're going to use, yeah.
Will we have our calculators for this?
No. Yeah, because I'm afraid you're just going to graph them. I know. All right, use the limit as x goes to 0 of sine x over x equals 1. We did that one earlier. We know that that's the limit. We're going to use that limit and properties to solve these other ones. That's an and properties to solve. All right, I've got 3 of these for you, and that'll be it for the day. Okay, so first one. We're going to find the limit as x goes to 0 for x plus sine x over x. All right. So let's talk about this a minute. You want to use direct substitution, you try, and it doesn't work. There's a 0 in the denominator, that's going to make you fail at this, right? And you can't have you don't have your calculator, so you're like, now what do I do? What you're going to do is you're going to break this up into things that you know how to find the limit of, okay? So this right here, we're going to rewrite this, and I know it's tedious, but you do have to write the limit each time that you're simplifying anything here, because it is the limit of it. So this is the limit of, and let's split this up. So x is being divided by x, and sine x is being divided by x. So we can write this as x over x plus sine x over x. Are you okay with that? I just took that fraction and I broke it down into two parts, x over x plus sine x over x. And now we're going to take the limit and we're going to kind of like distribute the limit, because this is like f of x and that's like g of x, and we can split them up and take their limits individually. So I can simplify this. What is x divided by x? It is. It's 1. Plus the limit as x goes to 0 for sine x over x. And I'm ready to evaluate. So what did we say about constants? The limit as x goes to 0 of 1 is 1. It's our little constant property that says if it's a constant, it's just going to equal that number. And then they gave us this. The limit as x goes to 0 of sine x over x was also 1. And so our answer is 2. Pretty good, huh? Something super complicated like that we don't know how to find the limit of, and we use our properties and break it down. All right, yeah?
How'd you get the sine x over x equals 1?
Oh, that was given.
Oh.
Yep. Yeah, because you don't know that. I mean, we graphed it earlier, but you wouldn't know that. You wouldn't remember it. You don't have to memorize that. No, always.
Oh, always?
Yeah, so we're going to use the fact that the limit as x approaches 0 of sine x over x is equals to 1 to answer these problems. So we're trying to get that in our answer, really, to evaluate. Okay, so let's do this next one. This one, you're going to love this one. All right, how about the limit as x goes to 0 for 1 minus cosine squared x over x squared. All right. Now, did this mention cosine at all in this problem? No. It was all about sine, right? Sine of x. So maybe we should use some properties that we learned way back in chapter 5, and we can replace 1 minus cosine squared x. Again, you know them. Yes, you should. What is, well, cosine squared plus sine squared equals 1, right? Pythagorean identity, that's the one everyone remembers. If you're going to remember one of them, remember that one, okay? You might not remember your double angle formulas or your sine, cosine, sine. You know the cheer, but you might not remember what it's for. But this right here, you know. What is 1 minus cosine squared? Sine squared. Yes, if we were to subtract cosine squared to the other side, you would get sine squared. Okay, so this is sine squared x over x squared, which we can then rewrite as the limit as x approaches 0. We can write this as sine x over x times sine x over x. Oh, see that? So sine squared x is simply sine x times sine x, and x is x times x. And so then we can take their limits individually, right? It's like distributing that limit to both of them. So what is the limit as x approaches 0 of sine x? It's 1, and then also times 1. So your answer is 1. Yeah?
You need to like show all that?
Yes! Yes! I mean, I do a little extra, but I would like you to show at least here, and then you can probably see it. Yeah. But at least show that. I'm cool if you can do the rest in your head. That's fine. Okay. I've got one more of these. We have time? Yeah, last one. It involves a radical. That's why I wanted to do this one. So the limit as x approaches 0 for the cube root of sine x over the cube root of x. And you get to something like this, and you're like, holy cow, that's so complicated. It's really not that bad. Okay? A lot of times you want to simplify whatever's inside of your limit first to try and make it more manageable. So I can rewrite this as the limit as x goes to 0 of the cube root of the whole thing. Put it into one cube root. Because they're both cube roots, you can rewrite it like that. Now, you remember that property I gave you? You can bring that cube root outside. It's so weird, but this is the cube root of the limit as x goes to 0 of sine x over x. That's what that property says. I know, it doesn't feel right to me. I don't know, it's weird. But you can take that cube root and put it around the whole thing. And we are given the inside. What's that limit again? It's 1. And the cube root of 1 is 1. All right. Enjoy your limits tonight. Tomorrow, though, is really the best lesson of the year.
Is it harder?
Yes.
That's not